More than 70% of Australia's land is arid or semi-arid. In many districts, heat climbs above 45 degrees Celsius and water remains scarce. Still, agricultural exports exceed 45 billion United States dollars a year. The answer begins with organization: fewer hands, larger paddocks, tighter schedules. The main cropping belts sit nearer the wetter southeastern and southwestern regions, while the interior stays far drier. Sheep shearing sheds rely on powered cutters. Drones track cattle across remote stations. Robotic dairies log milk flow, and large harvesters run through long shifts. Machinery, data, and automation already sit inside daily farm work, but the path into that shift still needs dissection. The shift into machinery starts with a harder debt beneath it. Australia is separated from major markets by thousands of kilometers of ocean, so every farm output carries distance before it carries profit. Nearly 70% of the country falls into arid or semi-arid zones. Dry ground first, logistics next. That pressure began long before tractors and sensors. Over millions of years, much of the continent's surface weathered under stable, ancient landscapes, leaving many soils poorer in nutrients than farming belts across Europe and North America. More than 1/3 of Australian rainfall also falls on a narrow coastal strip, which leaves the interior without the dense field pattern common in wetter European regions. The land never offered an easy grid. Then the climate adds speed. Droughts run longer, bushfires cut through grazing country, and heat waves raise demand for already limited water. Australia answered with scale, machines, and agricultural science, not small crowded farms. Huge holdings, long shifts, fewer hands. More than 350 million hectares are used for agriculture and livestock, in a country of about 27 million people. Next, that model has to be seen on the ground. At ground level, the scale turns into hand pressure and blade control. When a flock holds thousands of merino sheep, shearing becomes a time sequence where every second and every pass changes the result. Merinos are usually shorn once a year, so the shed concentrates months of fleece growth into a few crowded days. The clock is already running. Electric clippers wait at each stand, and sharp metal blades buzz against dense wool with the oily smell of lanolin in the air. The first scene is containment. Sheep move from the yard into holding pens, then one animal is drawn onto the shearing floor and set against the shearer's legs. The body is not pinned down by force. It is positioned so the spine, shoulders, and hips give fewer chances for sudden twisting. That control protects the animal and keeps the blades moving close to the skin. One slip wastes fiber. A modern handpiece resembles an enlarged electric hair trimmer, but here the cut must follow a living surface that shifts under the operator. The sequence starts on the belly because that wool is shorter, dirtier, and handled separately from the main fleece. The first passes clear the lower body, then the machine moves through the hind legs, hips, back, shoulders, and neck in long strokes. One hand guides the clippers, the other rotates the sheep enough to expose the next strip without lifting the animal into panic. The sound stays steady, a dry metallic buzz under the shed roof. Fine merino fiber often falls below 24 microns in diameter, so clean removal helps decide which bale enters a better textile grade. Then the fleece comes away, not in scraps but as one heavy mat, open from the sheep's body and carried to the sorting table while belly wool and stained edges stay apart. Classers spread it flat, pull out dirty sections and impurities, then grade the wool by fineness, fiber length, and color. An experienced shearer can process between 100 and 300 sheep in a day, and Australia's annual wool output is estimated at about 279.4 million kilograms. The removed fleece moves onto the sorting table, where clean and contaminated portions begin forming the commercial flow for the next link. From the sorting table, the scale jumps from hands to horizon. On cattle stations covering hundreds of thousands of hectares, a missed water point can cost more than a late job in the shed. Why does a station manager move from horses and pickups to drones and field robots? Because distance turns small faults into direct losses. The drone lifts over burnt grass, rotors making a dry rasp in hot air. Heat trembles above the track. First comes the water point, trough level, pump access, cattle pressure around the edge. Then the camera follows the fence line, looking for gaps, fallen wire, or damage that would take hours to find by pickup. Empty wheel ruts run through dust below. The next pass looks for animals split from the herd. Thermal cameras help separate warm bodies from pale ground, especially when scrub and distance hide movement. After drought, the same flight checks pasture cover, bare patches, and grazing pressure. Less driving, fewer blind spots. Some stations report annual savings savings of tens of thousands of dollars by cutting fuel use, labor time, and livestock losses. The national scale makes the control problem sharper. In the 2024 to 2025 financial year, Australia held about 29.7 million head of livestock, including about 27.6 million beef cattle. Livestock sales reached about 20.5 billion United States dollars. Anna Creek Station alone covers more than 2 million hectares, often cited as the clearest example of station scale. The robot adds a slower layer on the ground. Swagbot, developed at the University of Sydney, monitors cattle health, assesses grass quality, and helps guide herds toward better grazing areas. For the farmer, the equation is water, wire, animals, pasture, and time. As the rotors fade, an empty water point, pale tracks, and the distant horizon remain before the same heat becomes the next problem on fields and greenhouse control loops. That same dry heat now shifts into the Murray-Darling orchards, where distance gives way to timing. From February to April, growers get an advantage from dry air only after the almond hull splits, and before late rain reaches the rows. The Murray-Darling Basin covers more than 1 million square kilometers, spreading across several southeastern jurisdictions. One shower can change the crop. At maturity, the outer hull opens and exposes the harvest clock. If unseasonal rain wets fallen nuts, mold risk rises. If they stay on soil too long, kernel quality drops. The machine moves in because the window is narrow, not because the orchard is simple. The trunk is the trigger. A tree shaker closes a hydraulic arm around the trunk. The grip uses a soft rubber pad, so vibration transfers into the wood without cutting bark. High-frequency shaking travels through branches, and thousands of almonds break loose within seconds. Dry knocks hit the ground. The operator controls force and duration for each tree. Too little shaking leaves nuts hanging. Too much can crack limbs and reduce next season's bearing wood. Under the machine, dust lifts around the tires and pale shells scatter across the orchard floor. The sound is hard and dry. Then the pace slows, but the risk stays. Almonds lie under sun and wind until moisture falls, while the orchard rows rustle through the drying period. Sweeping machines push the crop into long windrows. A pickup harvester lifts the line onto conveyors. Inside the harvester, cleaning begins before storage. Air blowers separate light leaves and husks, while vibrating filters reject twigs, soil, and stones. The clean crop moves toward bins with less contamination and less time exposed on the ground. Australia estimated its 2024 almond crop at about 164,700 metric tons of kernel equivalent, with 2025 to 26 forecast near 175,000 tons. Containers take the cleaned almonds while the dry window still holds. From the almond rows, the story shifts to Port Augusta, where dry air no longer stays outside the risk map. Here, sensors, pumps, fans, and screens hold water, light, and temperature inside one sealed growing complex. White light sits under the roof. The air feels wet, while fans and pumps keep a flat mechanical hum. Port Augusta receives about 250 millimeters of rain each year, a low figure for vegetable farming without heavy irrigation. Yet Sundrop Farms built its greenhouse tomato project in South Australia around a different bargain. 145 million US dollars. The site links hydroponic greenhouses, concentrated solar energy, and seawater desalination, so fertile soil and natural freshwater stop being the starting point. The contrast is sharp. Outside, the coastal region is hot and arid. Inside, tomatoes grow with roots held in substrate, not field soil. Mirrors concentrate sunlight for the energy plant, while desalination strips salt from seawater before it enters the crop cycle. Reverse osmosis is the common desalination method in modern plants, using pressure to push water through membranes. Salt stays behind. Clean water moves forward. The crop receives nutrients through drip lines, with flow rates checked by sensors near the plants. Drops arrive at the root zone, not across an open field where heat and wind can waste them. Computers track temperature, humidity, light intensity, and how much water the plants take up. When readings drift, automation changes ventilation fans, shade screens, and irrigation pumps before the crop feels the full stress. This is not open farming with better equipment. It is climate risk moved indoors, where every adjustment has a cost and every delay can change growth. More than 15,000 tons of tomatoes can leave the facility each year, grown in a place where rainfall alone would not carry the crop. The yield can exceed 400 tons of tomatoes per hectare. After Port Augusta, where pumps fed measured solution to roots, similar control reaches the dairy. Soft hoof steps now start the record for each cow and each milking. The contrast is sharp. Earlier, farmers moved whole herds into milking parlors on fixed routines, usually early morning or late in the day. Gates clanged, animals queued, and fewer rural workers had to keep the schedule moving. Now the cow enters by choice. A chip identifies her at the station, and sensors pull up her milking history before the arm moves. The machine first cleans the 4 teats, then checks their position one by one. Lasers and camera guidance steer the arm under the udder, and the milking cups attach separately to each teat. Quiet mechanics, close tolerances. During the cycle, the automation measures milk flow and milk quality while watching for abnormal signs, including inflammation or falling production. One robot can collect about 1,200 kilograms of milk per day, while average output often sits between 19.3 and 26.3 kilograms per cow per day. On Australian farms, 3 to 4 robots commonly handle herds of 150 to 240 cows. The old method grouped animals around the clock. The new method turns each visit into an individual check, with less waiting and more health information from the same act of milking. A change in flow can point to feeding trouble. A quality shift can warn of mastitis before major losses appear. Each milking is logged as milk flow, quality, and inflammation signs. From the robotic dairy, the accounting moves into the grain belt, where each strip of field becomes a separate record. A missed line is not just lost time. It can mix grain qualities before the truck leaves the paddock. One late rain can lower the class of a whole harvest because moisture and sprouting change how buyers grade the crop. Hours matter. Across Western Australia, South Australia, Victoria, New South Wales, and Queensland, harvest usually runs from October to January, so the same weather window stretches across 5 states. In the financial year 2024 to 2025, Australia exported about 34.8 million tons of wheat worth about 7.3 billion United States dollars. That scale cannot wait for hand labor or simple machinery. The header cuts the crop, the threshing drum hums, and grain separates from straw inside the combine. Dust trails behind the machine in a pale wake. The unloading auger swings over a truck body while both vehicles keep moving, with short pauses only when a row ends or a turn begins. GPS guidance keeps the passes straight, reduces overlap, saves fuel, and lowers the chance that standing crop remains between lanes. After the run, yield monitors write the field as zones, not as one flat result. Then the map appears. Strong grain, weak nutrition, and poor patches show up in different colors, guiding next season's variety choice, fertilizer plan, and soil work. Modern receival standards also test wheat for protein, moisture, screenings, and contaminants, so field data can support real-time sorting into baking wheat, feed wheat, or export-grade grain. The older harvest ended with samples and laboratory results after the bins were already filled. The current pass collects grain and evidence at the same time, under weather pressure that does not wait for paperwork. A paddock can still look uniform from the road, but the map shows how uneven the crop really was. After the auger folds, the field lies empty behind the combine, while the yield map shows harvest zones, but not the soil's remaining reserve. The wheat map leaves one problem unresolved. Data can show zones, but heat still changes the crop before processing. In Riverland and Barossa, the next clock starts before sunrise. Cold hours matter. Across hot parts of Western Australia, picking time decides how the berry reaches the winery. In 2024, Australia produced around 1.43 million tons of wine grapes, up 9% from the previous year, still below the 10-year average. This is not one winery's timing problem. It touches a national volume of fruit. By late southern hemisphere summer, afternoon heat warms juice, speeds oxidation, and can push crushed berries toward early fermentation. Yeast on grape skins can begin feeding on sugar once warm juice leaks out. That is the danger. Headlights cut between rows before dawn, while cool air hangs low and dry leaves rasp against the machine. The harvester enters the row and straddles the vines. Shaking rods vibrate the canopy, knocking ripe berries from their stems without cutting the whole plant. The hum rises. Conveyors catch the fruit, while built-in blowers blast out leaves, twigs, and light debris in the same pass. Clean berries move upward into bins or a waiting trailer, ready for fast transport before the day heats the load. Machines cover large commercial blocks far faster than hand crews, which keeps cost and quality under control for many wine styles. But hand harvesting remains in old vineyards and premium parcels, where intact bunches, waxy bloom, and fewer bruises still matter. The split is sharp, speed for volume, fingers for delicate clusters. At the last row, the harvester unloads cool fruit fruit, and the truck turns straight toward the crush pad. After the vineyard race ends at the crush pad, the same pressure moves north into warm shrimp ponds, not hours before sunrise, but oxygen, pH, and what settles after feeding. On the surface, the pond looks almost calm. Muddy water ripples under paddle wheel aerators, shrimp break the film in quick splashes, and at the bank there is the heavy smell of organic sludge. That is the visible layer. The danger sits lower. Older pond management begins with the farmer's eye. Watercolor, feed trays, aerator noise, and the first signs of shrimp stress. It is experience under pressure. Modern control starts beneath that surface, where uneaten feed, waste, and organic silt collect on the bottom. As bacteria break down this material, dissolved oxygen falls, and toxic gases can build in the sediment. One missed drop matters. Growth slows, survival falls, and a profitable harvest can turn into a loss before the surface looks wrong. The frame shifts downward. Dark sediment, suspended organics, then probes reading dissolved oxygen in real time. Data replaces guesswork. Operators track oxygen, pH, salinity, and temperature, while aeration adds oxygen, feed management reduces leftovers, and water monitoring flags stress before shrimp crowd the edges. In the warmer north, especially Queensland, this matters because much of Australia's prawn farming sits in conditions where heat can push water quality quickly. Black tiger prawns are a major farm species there, and disease control shapes daily decisions. Some farms now move toward recirculating aquaculture, where water passes through filtration, treatment, and reuse inside a controlled loop. It costs more to build and run, but it gives farmers tighter control over waste, oxygen, temperature, and disease risk. The sector's value shows the bet. From around 56 million US dollars in the 2016 to 2017 financial year to around 153 million US dollars in 2022 to 2023. After grapes and shrimp ponds, the wider pattern tightens. From machine-sheared merino sheep to tomato greenhouses fed by desalinated seawater, the same rule runs across the sector. More than half its land is in farm use. Cattle stations are watched by drones and algorithms. Wheat fields move toward automation. Vineyard crews cut fruit before dawn. In dry country with poor soils and extreme weather, output depends on timing, water, machinery, and data. That control helps Australia produce millions of tons of farm goods each year, but the next weak point sits below every tire and root, the thin topsoil not yet seen in close-up. The first close-up of that top layer came over Sydney in 2009. Sydney Red Dawn lifted 75,000 tons of topsoil in one day, and red dust turned the sky a burnt orange. The air tasted mineral. So why does rain not simply repair the field? The answer starts before the storm, inside the material itself. The Millennium Drought ran for 12 years, leaving dry riverbeds, open cracks, and a hard crust that crunches under boots. Australian soils are often old and naturally low in phosphorus, so lost surface material is not replaced quickly by fresh fertility. Less cover means less grip. Loose grains remain exposed. Then Black Summer removed another layer of protection. In 2019 and 2020, fire fronts crossed more than 18 million hectares, larger than the United Kingdom, and burned vegetation that had held soil in place. A camera drops to ground level. Ash, bare roots, exposed mineral grains. After fire, waxy plant compounds can coat soil particles, creating hydrophobic layers. Water hits that surface and beads instead of sinking. Raindrops gather, slide, and become sheet flow, carrying fine particles downslope before roots can use the moisture. The field looks wet for minutes. Beneath it, the profile stays dry. After the rain, there is almost no sound, only drops moving over a hard surface and a dry layer left uncovered. After the dry surface is left exposed, the next risk lies in the residue itself. Each year, Australian wheat fields hold around 28 million tons of straw after harvest, more mass than the country has people. Australia has about 26 million residents. That number lands hard. The process starts in the windrows. The harvester cuts grain and pale straw drops behind it in long, dry bands. Under summer heat, the stalks crackle when crushed, and bales can trap warmth inside their cores. If the internal temperature rises above 70 degrees Celsius, dry straw can ignite without a match. Then wind changes the scale. material. A smoldering bale breaks apart and glowing fragments move across stubble. The fire front can run 2 to 3 times faster than a typical forest fire because the fuel is light, dry, and already spread across the field. One spark becomes a moving line. Farmers face a hard disposal problem after harvest. Many choose burning because it clears paddocks fast and reduces residue before the next pass of machinery. But the material does not vanish. Each ton of burned straw releases about 1.3 tons of carbon dioxide, along with carbon monoxide and fine particles. The smaller particles matter most near roads and towns. PM 2.5 means particles up to 2 5/10 micrometers across, small enough to reach deep into human lungs. During harvest season, acrid smoke hangs over rural districts, and a gray-white suspension collects near the roadside. Visibility drops in minutes. This is why straw becomes 2 risks at once. On the field, it can carry flame faster than crews can cut a brake. In the air, it turns into gases and dust that trigger warnings and traffic crashes. Farmers light the rows and the smoke moves out toward the roads. After the fires and the smoke trail, researchers turned back to the residue itself. By the late 1980s, CSIRO teams and Western Australian research groups were spreading straw across field soil, then measuring heat and moisture. Same material, opposite result. The contrast was physical, not symbolic. Bare soil took the sun directly, heating into a hard crust at the surface. Under straw, the top layer stayed cooler and softer to the probe. A thermometer enters exposed ground. Another enters covered ground. The gap can reach 10 degrees. CSIRO is Australia's national science agency, founded in 1916, and its fieldwork gave the change a measured frame. During the 1990s, experiments confirmed that straw mulch slowed evaporation and held water 2 to 3 times longer on the same land. That mattered because soil microbes need thin films of water around mineral grains before they can break down residue and cycle nutrients again. The field did not become repaired by appearance alone. Under the straw, moisture lasted long enough for microbial life to restart in the upper layer, while the cover also reduced wind contact with loose particles. Less heat, less water loss, more biological activity near the surface. In wheat belt studies, the effect reached the crop. Some trials recorded yield gains up to 8.7%, while the same cover reduced wind erosion across exposed rows. The number package was clear: minus 10 degrees, water 2 to 3 times longer, and yield gain up to 8.7%. Those field numbers pushed the trial beyond ordinary paddocks, into country where farming was already slipping away. Around 70% of Australia sits in arid or semi-arid zones, across a landmass of about 7.7 million square kilometers. In summer, bare ground there can rise above 60 degrees Celsius, and a dry gust can lift the upper soil layer in hours. The margin is thin, so the question moved from yield to survival. Bales left wheatbelt farms and traveled tens of kilometers into degraded country, past fence lines, salt scars, and cracked surfaces. Trucks unloaded straw onto ground that felt hard underfoot, with dust moving low around the ankles. Crews spread it across exposed patches, not as fertilizer first, but as cover, a physical shield. The mechanics were simple, and that made them useful at scale. Straw roughened the surface, so wind speed near the soil dropped before grains began to move. It shaded the crust, slowed evaporation after short rain events, and held moisture where bacteria and fungi could restart decomposition. On test plots, evaporation fell by 35 to 50%. Within a few months, researchers recorded a clear rise in soil microorganism density. The change began in the lowest few centimeters, where desertification usually wins first. Under the straw, air moved more quietly, the soil stayed cooler, and rare water did not vanish from the surface so fast. The cover also reduced sand drift and helped stabilize thin topsoil damaged by erosion and salinization. Not a miracle, a microclimate. Then the strongest evidence appeared without machinery. On some plots, grass seedlings returned after many years with no visible growth. Small green shoots breaking through straw on land that had been bare for seasons. Those green shoots mattered because older soil defenses had failed under the same filter. Heat above 45 degrees Celsius and rainfall below 250 millimeters. The story turns backward. Before straw reached degraded ground, Australian farmers tested barriers, fences, trees, imported grasses, and rough surface cover. In the Mallee districts and near the semi-desert belt by the Nullarbor, windbreak fences came first, tree lines followed. The goal was simple: slow the hot wind before it stripped loose topsoil within hours. But young trees needed years to form a working barrier, and the climate gave them weeks of stress. Leaves browned, roots stalled, the barrier never closed. Cover crops looked stronger on paper, especially after success in the United States and Europe. In those regions, seedlings shield soil, feed microbes, and hold moisture between crops. In the dry Australian test zones, the sequence broke at the first step. Seeds germinated, then withered as surface moisture vanished. No canopy formed. Bare ground stayed exposed. Farmers also tried branches, coarse material, and contour furrows. These were cheap, visible fixes built directly onto the surface. For a few weeks, they slowed moving dust and trapped scraps of moisture. Then heat opened cracks, wind shifted the loose cover, and the lines lost shape. Temporary protection disappeared. Even drought-tolerant grasses caused trouble. Buffalo grass, Cenchrus ciliaris, entered Australia as a fodder and anti-erosion plant, but later spread into parts of the arid interior. It displaced native species and added dry fuel. Fire risk climbed, so the old threshold remained. Rainfall under 250 millimeters, heat above 45 degrees Celsius, and soil still lying open. That same straw, left on the paddock to shield soil, also carries a harder energy number. In Australia, collecting only 20% of the annual straw crop is linked with replacing about 5 to 7% of transport fuel demand. That is the shock. The dry stems now move into a chain where chemical bonds set the limit on usable energy. After harvest, the field is pale and brittle, and every step through stubble gives a dry rustle. Wheat straw looks simple, but it carries a high share of cellulose inside lignocellulosic mass. Cellulose, hemicellulose, and lignin bound in the plant wall. Cellulose is a chain of glucose units. Hemicellulose breaks down faster, and lignin stiffens stems while blocking enzyme access. At CSIRO, the Commonwealth Scientific and Industrial Research Organization, and Australian universities, researchers pre-treat that structure so microbes and enzymes can reach the sugars. The target is controlled biochemical breakdown, not weathering. One route ferments those sugars into bioethanol for transport fuel. Other pathways produce biogas and hydrogen. The margin is tight. Too little breakdown leaves carbon locked, while contamination cuts yield. Then heat takes over. In a gasification unit, straw enters a hot reactor with limited oxygen, and the dull industrial noise replaces the field's dry scrape. A gas flare marks the outlet, where syngas carries carbon monoxide and hydrogen for electricity generation, heating, and fertilizer raw materials. So straw gains a second role after soil protection. It can stay where erosion risk is high, or enter a measured fuel chain where removal rates matter. Too much collection strips fields, too little limits output. 1/5 of Australia's annual straw can cover up to 7% of transport fuel demand, and the route now shifts from Australia to the United States. From that fuel equation, the trail crosses the Pacific into older damage. In the 1930s, the Dust Bowl stripped the United States of more than 40 million hectares of soil. Topsoil gone, farms exposed. Today, the country still produces more than 150 million tons of cereal residues each year, including wheat straw, corn stover, and other harvest leftovers. Yet millions of tons of straw still burn on fields after harvest, turning stored carbon into smoke and ash. California pushed restrictions on straw burning because fine PM 2.5 particles cut air quality, lower visibility, and raise wildfire risk. This is not memory, it is a present engineering problem. California's limits show that straw burning has become an air and fire issue, so the next step is practical use. With more than 150 million tons of grain residues and tighter burn limits, the answer moves into hardware. Kansas turns wheat straw into bioethanol, while the Southwest packs the same material into house walls. At a Kansas plant, straw arrives dry, pale, and stiff. The stalks are chopped, pre-treated, then pushed toward fermentation. Fast chemistry. Cellulosic ethanol depends on breaking cellulose into sugars before microbes convert them into fuel. At the Department of Energy, research teams study lignocellulosic structure because lignin protects the plant fibers and slows that breakdown. Cleaner fuel starts inside the stalk. Then the material changes job. In Arizona, New Mexico, and other hot, dry states, builders stack compressed straw bales into thick walls. The bales crackle under pressure and loose fibers rasp across a glove. These homes are not a novelty from nowhere. Straw bale building has been known in the United States since the late 19th century, with early examples in Nebraska. The physics is simple. Trapped air inside the packed stems slows heat transfer, so rooms stay cooler in summer and warmer in winter. Lower heat flow means lower demand for cooling and heating. The bales can fill a frame, or they can form the wall blocks themselves. Plaster seals the outside, adds weather protection, and gives the finished wall a dull thud under a knuckle. Same straw, different load. It leaves the field as transport fuel in Kansas, then becomes insulation in dry state housing. Pressed into bales, closed behind plaster, and moved from field to home, it sets up the next question: how all these uses combine on soil, emissions, and dry land farming. After Kansas, Arizona, and New Mexico, the chain closes around one residue. Straw can protect soil, feed energy, and fill walls in dry regions. The contrast is sharp. What was once burned on open fields now helps hold topsoil, slow desertification, reduce emissions by avoiding fire, and replace part of conventional fuel. Across wheat districts and semi-arid plains, the same material changes role according to climate, cost, and local pressure. Australia, the driest inhabited continent, makes that logic urgent, but the pattern also reaches the United States and other farming nations. 4 functions remain: soil held, desertification slowed, emissions cut, energy supplied. After harvest, the field stays pale, open, and without smoke.